Okay, so the second part of vectors we're going to look at, it's still 5.4 on that PDF, so it's going to be the same PDF as last night. We're just doing the second part of it. So let's suppose that we had two vectors, and I'm naming the two vectors v and w. So remember, these are bold. And each vector has a horizontal and a vertical component. So what I want to do is define what it means for two vectors to be equal to each other. So when we talk about vectors, when we say they're equal, it doesn't mean that they're in the same position. Okay? For example, if you had this vector, and then you make a copy of it, and you put it somewhere else, those two vectors are equal. Do they have the same start point?
No.
No. Do they have the same terminal point?
No.
No. That's not what it means for them to be equal. It just means that if you were to measure them, the horizontal components and the vertical components are exactly the same. Okay. So the horizontal component of the top one, I drew it, and I drew the vertical. Here's the horizontal and vertical for the bottom. And they're the same. So essentially, you're making the same triangle when you draw those components. But they do not have to start and end in the same spots. Okay. Any questions on that idea? What it means for two vectors to be equal? Yeah?
Can they be going in different directions?
No, they have to point. They have to point in the same direction. Yeah. So that's a good point. Yeah, because if they were pointing in the opposite direction, then the horizontal and vertical components would be the negatives of the original. They have to be exactly the same. Okay. Any other questions on that? Okay. So I told you that we're going to be kind of getting away from drawing. We're going to look at different notations we can use to write vectors without drawing. I showed you one yesterday where we had the angle brackets, and you have two numbers in the middle with a comma. Today we're going to look at what's called unit vector notation. Does anybody remember, I might have said it yesterday, that there are two vectors, well there's three, but we're talking in 2D, there's two vectors that have special names, and you don't want to use those two letters per vector.
I, H, or
I was one of them, yep. And J was the other one. K is when we get to 3D. But yeah. So we're going to look at two special unit vectors. Okay. First one is I. Okay. I is a unit vector, and it points to the right. So if you want to see a picture of what it looks like, that's what it looks like. That's called an I. I can't be anything other than that. So if you want to name a vector, pick a name besides I, and pick a name besides J. J is always defined to be a vector that's 1 unit long and points up. J cannot mean anything else. Okay, here's a picture of what J looks like. It's 1 unit long, and it points up. So what we're going to do is we're going to take I's and J's, we're going to stack them together, and we're basically going to like build a vector using I and J as like building blocks. Okay, that's the idea. And when we do that, it'll lead us to unit vector notation, which is the most common way people write vectors other than sketching. Yes?
Sorry. Will we ever be using, well, for this, that we're doing, will we ever be using like the graphing utility like for the vectors to like show them at all?
No. No. Okay, so let's sketch the vector 3, 4. So what doesn't this tell me about the vector?
The starting point?
It doesn't tell me the starting point. Starting point doesn't matter. Start right there if you want. But from that point, how do I get to the terminal point? You can think of the 3 and the 4. They're like directions.
So
Yeah?
you go like right 3 and then up 4.
Right 3, up 4. Okay. Now, what I want to do is, starting at the initial point, I want to stack as many i's as I need to start getting me lined up with the terminal point. So how many i's would I need to stack together, starting at the initial point, to move me towards the terminal point?
3.
3. So I'm just going to draw that. I need 1, 2, 3. What do you think you would call that bottom vector? There's kind of a name for it if you stack 3 i's together. It would be, yeah, that's 3i. That's the first part of how you write this vector as what's called a unit vector. 3i, plus we need to stack something on the end of it. How many j's do we need
4.
to get up to this terminal point? How many? 4. So 1, 2, 3, 4. And what do you think you would call that vector? 4j. So if you put 3 i's with 4 j's, that's how you build the vector 3, 4. And that's called unit vector notation. So it's basically the same as the notation we just had, except you get rid of the comma and the angle brackets, and you put an I and a j after the 3 and the 4. So 3 i's plus 4 j's. Now, I moves you right and j moves you up. But what if you had to do a vector like this? You still have to go to the right. So that's 4i. But what do you think we would do with the j's? Yeah?
You subtract 3.
Yeah, you'd subtract 3j because you gotta go down. So it's negative j, negative j, negative j. That's negative 3j. So by letting I and j be positive and negative, you can move any direction you need to on the coordinate plane. What you can't do with I and j is move in and out. That's 3D. To do that, we need one more vector, and that would be k. And we'll see that on Thursday. But I and j allow us to do everything we need to in 2D. Any questions on that? So that's called unit vector notation.
Do you just say 0i plus 0j for like for when it like cancels out to like 0?
To win for the 0 vector? Yeah. Yep. Anytime you're missing a component, you could all, like if you just had 3i, you could say 3i plus 0j. Yep. All right, so let's look at some different formulas for vectors. In these formulas, v and w are going to be 2 generic vectors with horizontal and vertical components. And alpha is going to be a scalar. Not sure why they use a Greek letter for the scalars. They just do. What are the 3 things that can happen when you scale a vector? Yeah?
You can increase its length, minimize its length, or reverse the direction.
Yeah. Yep. So those are the 3 things. So let's start with how we add 2 vectors. We already know how to do it visually. You take one, you put the other one on the end of it, and then you connect the diagonal. If you want to do it with just numbers, all you have to do is take the horizontal components of your 2 vectors, add them up, and then take the vertical components of your 2 vectors and add them up. No sketching at all. Subtraction is pretty much the same idea. If you want to subtract 2 vectors, Visually, kind of a pain. You got to take the second vector, you flip it around, and then you add it. Numerically, very simple. Subtract your horizontal components, subtract your vertical components. When you are subtracting, does the order make a difference, or does it not matter? Yeah?
It does make a difference.
It makes a difference, yeah. Subtraction is not commutative. You can't switch the order. Addition, though, you could. If you switch the order, you'll still get the same answer. Okay, so the next one is a scalar. If we were going to scale a vector by drawing, let's say we wanted to do 12v. We could take v, you'd copy it 12 times, stack them all together, that would be 12v. When you're doing it numerically, all you have to do is scale each component of the vector. So if this was a 12 on the outside, you'd multiply each component, horizontal and vertical, by 12. It's kind of like a distributive property with your scalar. And the last formula, we talked a little about it yesterday. What does it mean when you put a vector inside double bars? Yeah.
You're only searching for the magnitude?
Yeah, we're trying to find the magnitude. And if I had a vector like this, actually I can just go back to the page we just had. Let's look at like the one in black. If you wanted to find the magnitude of the black vector, it's kind of laid out how you would do it. But then you want to kind of have an idea how you would find the magnitude of the black vector? Yeah, you just treat the vector as the hypotenuse in a triangle. You draw in your horizontal and your vertical components, which are your i's and j's, and then use the Pythagorean theorem to get the magnitude. So it's the horizontal component squared, vertical component squared, add them up and take the square root, and that'll give you the hypotenuse. Okay, so it's just Pythagorean theorem. So we'll take a look at, we'll do each of those. Okay, we'll give you some numbers and we'll go through all of them. Okay, I'm also going to have you practice writing your answer with the algebraic notation and unit vector notation. Okay, we'll try both. So here's a couple vectors, unit vector and the algebraic notation we learned yesterday. Okay, so the first thing they want us to do is v plus w. No sketching. Don't sketch it. Okay. So if you were to add these two vectors together, can somebody give me the answer in unit vector form? Yep.
Root 5i minus 1j.
Yep. You can say minus 1j. You can also just say minus j. How about, can someone else tell me if you rewrote it this way? What would it be in that notation? Now you do need to put a number here. Yeah.
-1.
Right, now you have to put the -1. Yeah. So both answers are correct. It's just a matter of what the directions ask for. Right. Let's look at subtracting. How about v minus w? What's v minus w? First, as a unit vector notation.
-I, 7j.
I.
7j. 3 minus -4 is 3 plus 4.
So tell me how you write your final answer.
V minus w. For, in the like bracket form or the I and J form?
Unit vector.
The second?
No, I and j.
So that would be -I, 7j.
What's the sign in the middle of the middle?
Oh, plus of j.
You gotta have the plus there. So -I plus 7j. Or, how about in what the book calls algebraic form. Yep,
Negative 1, 7.
-1, 7. I don't know why they call it algebraic form. There's no letters in it. Usually algebra has letters.
Could you treat the left side as like a full equation and actually like plug it into like a formula to like find information about like a circle or a triangle or something? Like, can you use that in that form?
Well, you can use these numbers as like the base and the height of a triangle to find the magnitude. Yeah. Which would be the radius of a circle, if you think of it that way. So, yeah, there's all kinds of connections and things here.
I'm only asking because usually when we're given, like, because like obviously we've been given x, y, and like this and formulas for x and y, but like that is actually making an equation that you can literally move x and y directly. Like
Yeah.
instead of just saying like the point, somehow making an x, y equation. So I'm just wondering if there's anything more special that's with that.
Okay, how about 3v? What do you think 3v would be? Yeah. 6i plus 9j, or 6, 9, either one. And what about the magnitude of v? I'm looking, really, I don't want the final answer yet. I'd like to see the calculation to get magnitude of v. Yep.
6 squared plus. I thought we were doing the diagram theorem.
So say it again.
Are we doing like the diagram theorem one?
Yeah, for vector v. Yep.
So wouldn't it be 6 squared plus 9 squared b squared?
Not for vector v, no. Yep.
The square root of 2 squared plus 3 squared.
The square root of 2 squared plus 3 squared. Yep. You were doing the magnitude of 3v. Yeah. So magnitude of v, 2 squared plus 3 squared. Square root of 13. As always, you have to make the square root as simple as you can. Right? So if it's like square root of 20, I'd be looking for something like 2 root 5. If they say you could round it to a decimal, then round it to a decimal. Otherwise, I leave it as an exact answer. Because we're going to be doing something with this magnitude tomorrow, having to do with angles. So the more accurate the magnitude is, the more accurate the angle is going to be. So just leave it as a square root, unless they say no. Okay. Any question on that? So that's an example of each thing, each formula. Okay, so if the magnitude of a vector is 1, we talked about that yesterday. That's a unit vector. What I want to look at is what can we do to a vector to turn it into a unit vector if it's not? Well, if it's too long, we've got to make it shorter. If it's too short, we're going to make it longer. But I want to know exactly. I want like a formula. So let's look at some examples.
Would it possibly have absolute value in it?
No absolute value that I can think of. So let's say the length of a vector was 5. What would you scale it by to turn it into a unit vector? Yeah? 1/5. I'm going to say that a little differently. 1/5. Okay. How about if the length was 3? Yeah?
You would just multiply it by the reciprocal.
Yes. You always end up multiplying it by the reciprocal of the length. So if your length was, say,
It would turn out to be like v over v.
so yeah, if your length was 1/2, you'd have to scale it by 2. So you scale it by the reciprocal of the length. If the length was already 1 and you scale it by the reciprocal of 1, well, nothing changes. But that's the pattern. Yep. Scale by the reciprocal. So if this was your vector, let's call it v, the reciprocal of the magnitude would look like this. I'll just write that like this. That's how you scale a vector, by the reciprocal of its magnitude. Or, if you want to put it all together, you can say it, I think, Jacob, that's maybe what you were kind of saying. It looks like that. That's the formula to find a unit vector. You scale it by the reciprocal of the magnitude. And that's the pattern you get just by looking at the table. So let's write that formula down. So if you want to write it again, there it is. A unit vector can be found by scaling a vector by 1 over its magnitude. So, in order to find a unit vector, the first thing you need to do is figure out, do you already have a unit vector? If you do, you're done. If not, tell me how long it is, and then scale it. Let's look at this one. Find the unit vector for 3i minus 4j. First of all, if you go 3 to the right and you go 4 down, do you think that would have a length of 1 unit?
No.
No. So then we need to figure out what the length is. Make a right triangle. And can anyone tell me what the magnitude of v is in this case? Yep.
The square root of 3 squared minus 4 squared, or the square root of 3 squared plus negative 4 squared.
Yep. And what would be your final answer?
The second one.
Yep. 5. Yep. So the magnitude of that vector would be 5. Yep. So that tells us what we need to scale by. Our vector is 5 units long. We want to turn it into 1 unit long. What would I scale that vector by to turn it into a unit vector?
Wouldn't we square root 5? Wouldn't it be the square root of 5?
It's the square root of 25. 9 squared plus 4 squared. So 3 squared plus 4 squared. So 9
Yeah.
plus
Okay.
16.
Yeah.
And then take the square root. So what do we have to scale by to turn this into a unit vector? Yeah. 1 over 5, 1/5. So it's going to be 3/5 minus 4/5. There you go. That is your vector. So it still points exactly the same direction as the original. It's just shorter to become a unit vector. And the reason why you might want to figure out a unit vector is because if you were trying to find the angle between those two vectors, it doesn't matter how long they are. You could work with shorter vectors and figure out the angle just as easy. And it might be easier to work with shorter ones. It's still the same angle. Yeah.
So you said for the unit vector, if it's 1, if it's either reciprocal, then it should just give you 1 again. So would you, for that final answer, technically that counts as the magnitude 1. So if you did the reciprocal of that, the new v, when you get like the old answer,
If you
not
scaled
like-
it by 5, yeah, it would change it back to what it was originally. Yep.
like if you did the square root of 3/5 squared plus 4/5 squared, you would get 1?
You get 1.
Huh.
Because you would have 9/5 plus 16/5. No, you'd have 9/25 plus 16/25, which is 25/25, which is 1. Yep. And square root is still 1.
Yeah.
All right, so 2 applications we're going to look at are a velocity vector, and then we're going to do a problem with forces. The velocity vector, this one's it is easier than the force one. Okay, so when we write down a vector, how many components do vectors have? In 2. Yeah?
2, it's like
2.
5. magnitude, or not magnitude, it's direction and
Well, the components are both directions. So in 2D, what are your directions? Right, yeah, horizontal and vertical, x and y. So when we want to write what's called a velocity vector, we're going to have to take a velocity and we're going to have to break it down into its components. Because the way they're going to give us a problem is they're going to say an object is moving, let me just kind of give you an example. Okay, an object is moving at 50 miles an hour at an angle of 30 degrees. That's not a velocity vector. There's no such thing as an angle in a vector. In a vector, you have a horizontal component and a vertical component. So somehow you've got to turn this information that they're giving you into a velocity vector. Okay, and that's what I want to, let me just go through it first, then we can, let me show you how we do it. So let's just generically represent the angle. I don't want to use 30. Okay, let's use like theta. Okay, so there's your angle. And this vector here, I'm calling it V. You can make it a bold V, you can make it a V with an arrow, however you want to do it. This is what I'm trying to find the formula for. This arrow. What do you think I'm going to do with that arrow to break this down into like a horizontal and a vertical? Yeah?
Just do the I's and J's again.
All right, so what am I going to draw to break this down into its?
The full triangle, like the X and the Y.
Yeah, we're going to make a right triangle by drawing a perpendicular from the terminal point straight down. So draw a perpendicular. I think that's pretty straight, like that. And now, if we can figure out basically what this vector is and combine it with this vector, the red and the green vector combined together give you the black one. But that's what you need to figure out. The red vector is basically going to be what goes in that box, and the green vector goes in the second box. We just have to figure out how long they are. So let's just temporarily call the bottom side x. And we'll call this y. What trig function could I use to find x? Yep.
Tangent. Opposite over adjacent. Because like y over x equals...
We don't know y, though.
Oh.
We don't know y, and we don't know x.
So you could technically do the law of sines or law of cosines thing?
Well, we have a right triangle, so we definitely want to, if we can, stick with the sine.
Angle, side, so that'd probably be law of cosines.
Well, it's a right triangle, though. So we want to stick with sine.
Pythagorean. Oh, sorry.
Yep.
Cosine of theta equals x over v.
All right. Now, can you be more specific? I understand when you say cosine of theta is x over, what about v? Like specifically, what about this side? Yeah?
The magnitude of it.
The magnitude of it, exactly. Right? It's cosine of theta is x over the magnitude, the length of that other side. So then if I get x by itself, what would be in that box? Yep.
It would be the magnitude of v times cosine of theta.
Perfect. Magnitude of v cosine theta. That is how you find the horizontal component of a velocity vector if they give you the angle that the object is traveling at and the speed that it's traveling at. The speed is the magnitude. That's what we talked about yesterday. So magnitude v cosine theta, comma. And does anyone have a guess what the formula is going to be for the vertical component?
sine. The same as sine.
Same thing, yeah, it's sine.
With y.
So magnitude v sine theta. Okay. And I'll write that out nicely on the next page. But that is the formula for a velocity vector written in algebraic notation. I can also write it in unit vector notation just by taking the brackets and the comma out and putting an I and a J. You can do the same thing. Okay, the important thing to remember is theta is the angle the object is traveling at, and the magnitude of v is the speed that it's traveling at that angle. Okay. All right, so let's, you know what? I already have it here, so let's just do it. So you can write it like that as a unit vector, or you can do magnitude v cosine theta and put an I, so that'll come out to a number with an I after it. Magnitude v sine theta j. There's two different ways to write velocity vectors, just algebraic notation on the top, unit vector on the bottom. Yes?
If you go back up, so are the x and y's magnitude technically as well?
X and Y were just names I picked for those two sides. It's not really important as long as you understand that this is the horizontal component. That's like X. This is the vertical component. That's the Y.
I'm just asking, sorry, but I'm just asking because I'm just.
The x and the y are already in magnitude form. Probably be x and y like that.
Yeah.
It's just I want to make sure there isn't like anything for position and vectors. Like, it's really.
Nope, nothing with position.
Darn it.
Okay, so I already gave you those formulas. I guess I can just clarify. This is the initial speed. But you should know that from yesterday. Magnitude is the speed. And you should know theta is an angle. All right, let's try it. So we have an object going 50 miles an hour at 30 degrees. When they give you an angle of 30 degrees, that's usually with the horizontal. So that means if this was the ground, it's 30 degrees angle of elevation. So it's going like that.
You wrote on that last slide initial velocity, but like, there's not going to be any change in velocity?
No, we're not going to let it change, because if it did change, it would be more complicated. When you throw something at an angle, the only part of the velocity that's really changing is the vertical. Because as something travels, it slows down at some point vertically and then starts coming back down. Except for air resistance, horizontal velocity never changes. Okay, so if you ignore air resistance, when you throw something, gravity doesn't slow it down horizontally. It's going exactly the same speed horizontally the whole time, except for air resistance. But vertically, it's not. If we take that into account, it gets more complicated. So technically, this is initial speed. But in our problem, it'll be the speed.
Okay.
Yeah. It is technically initial speed. Okay, so our speed is 50 miles an hour. The angle's 30 degrees. They want us to write that as a velocity vector. Okay, so break the 50 and the 30 into its components. Right. What's going to be the formula for my horizontal component? Yeah. And can you fill in the numbers from our problem? Say it again. We need a number though for that. Yep.
Would the length or the magnitude of the vector be 50, and then we'd have cosine 30? And if we're going to, which form do you want the Okay.
We'll do it, since I wrote the I, we'll do it that way.
Then it would be plus 50 sine 30.
Yep. And what comes after it?
Okay.
Okay. So we're really finding the base and the height of a triangle. That's all that a velocity vector is. All right, so we'll do 50 cosine 30. Make sure you are in degrees. 50 cosine 30. 43, we'll just call it 43.3. And what's the sine of 30? That comes out to a nice number. What's the y value for the coordinate for 30 degrees? Yeah, it's 1/2. And what's half of 50? 25. So that's your velocity vector. Now it says explain the meaning of each component. What is the 43.3? Like if this object was actually traveling 50 miles an hour at an angle of 30 degrees, what could you measure about it that would be 43.3? Yeah?
Like the distance of x. Like,
No, it's not a distance. The 43.3 is not a distance. Yeah?
Horizontal speed.
Yes, it's the horizontal speed. So like if you were standing in front of somebody and they threw something at you at 50 miles an hour at a 30-degree angle, and you had a radar gun and you pointed it at the object coming at you, it would be coming at you at 43.3 miles an hour. It's not coming you at 50 because they didn't throw it at a 0-degree angle. Some of the energy is going up, not just forward. And what would the 25J be? Yeah, that's the vertical speed. The second the ball leaves your hand. So if you were in like a helicopter over the situation and you pointed a radar gun straight down, the second the ball leaves the person's hand, it's traveling up to 25 miles an hour, but it's constantly slowing down because gravity is going to slow it down, and eventually it's traveling at 0 miles an hour vertically, and then it starts going back down. Okay, any questions on that? Okay, so that's how you find a velocity vector. Okay, so last problem. This problem is going to be about what we call static equilibrium. When you see the word static, what does the word static mean, like in physics? Yeah? Not moving. It's the opposite of dynamic. Right? Dynamic is moving, static is not. So static means we're looking at a situation where nothing is moving, all the forces are balanced. Because when forces are balanced, things don't move. Right? I'm holding this pen. It's not moving. It doesn't mean there's no force on it. Gravity's pulling it down,
Potential energy.
but I'm pushing up. So everything is balanced. Now in 2D, think of like a coordinate plane. How many different directions do you have? Well, like how many, like in 2D, how many axes do you have?
Two.
Yeah, 2 axes. You have a horizontal direction, and then you have a vertical direction. So if something is balanced in a 2-dimensional system, then that means it's not moving left and right, and it's not moving up or down. In 3D, it would also mean it's not moving in or out. That gets a little more complex. Okay, so let's take a look at the problem that we're going to do. So this is going to be a problem about finding the tension in 2 cables. Okay, and there's our diagram. So we have 1,200 pounds of weight being suspended from 2 cables. Cables are not the same length, and because they're not the same length, they don't make the exact same angles with the ceiling. Okay, they're different lengths. Also, it's important to understand you can have more tension in the cable combined than the weight of the object. Think of like a rope, like in tug of war. Maybe the rope weighs 60 pounds. But if you put 100 people pulling on each side, you could get a lot more than 60 pounds of tension in that cable. You could have thousands of pounds of tension in the cable. Even though the rope doesn't weigh thousands of pounds, it's because you're pulling against each other. And that's kind of what's happening here. These two cables are pulling against each other a little bit. All right, so what we want to start out with is kind of figuring out conceptually what's happening and then start to convert that into math. This object isn't moving. What direction is it not moving in?
Vertical.
Okay, it's not moving vertically. If it's not moving vertically, what does that mean about the force pulling it up and the force pulling it down?
They're equal.
They're equal. Okay, so the force, we'll just say it like this. The force that's pulling up is equal to the force that's pulling down. Okay, that's not very mathematical. It's just kind of conceptual. Okay, force up equals force down. What other way is this not moving?
Horizontally.
It's not moving horizontally, which means
Same thing, they're equal.
what's
Well,
equal?
Force left equals
The force of both cables.
Force left equals force to the right. So that's the initial part. How many equations did we just set up?
2.
2. How many things are we going to be solving for?
2.
2. Kind of sounds like a system of equations. You're solving, you're going to have 2 equations, and you're going to have 2 variables. So we're either going to do substitution or elimination to eventually solve this. Okay, we got to set it all up. All right. What I want to do now is look at the diagram, and I want to start to break these cables up into their components. Let's call this one, we're going to call one of them T1 and the other one T2, okay, for the tension in the cables. Let's call, I guess this one could be T1, and this one could be T2. Which way is cable T1 pulling?
It's pulling it to the left.
To the left and
Up.
up. It's pulling in 2 directions. So it looks something like that. Okay, it's pulling left and up. And how about T2?
Up and right.
It's pulling up and to the right. We know it's pulling to the right because if you cut T1, all of a sudden it would swing to the right because the cable is pulling it to the right. And it would fall down a little bit, but it wouldn't hit the ground. Okay, so how do you think I'm going to break T1 and T2 up into horizontals and verticals? What do you think I'm going to draw here?
I'd say vertically you would go where they intersect. So like at the at the initial point of T1 and the initial point of T2, and then go up from there.
Oh, okay, draw a line inside here.
Yeah.
Yeah, you could draw a line inside there. How else could I make right triangles besides putting it right there?
You can go from the terminal point of T1 down, and then
Yeah, we could go down. Okay, if we put another horizontal here, and then draw in a vertical and another vertical.
does it make a huge difference between them?
No, it'll just be easier to see this way, I think, because then I won't have 2 lines on top of each other in the middle.
Oh, okay.
Yeah. Okay, so if you combine that vector with that vector, that gives you T1. T1 is pulling left and it's pulling up. If you combine that vector with that vector, you get T2. So what we have to do is start figuring out what these green and red vectors are mathematically. Let's just give them a name first. This is a horizontal vector pointing to the left. What would be a good letter to use to name something that's horizontal? Yeah, so let's call this one x1. But we also have another x over here. So what could we call that one?
X2.
So let's call that x2. And what about the red one that points up on the left?
Y1.
So that'll be y1. And on the right, y2.
They're the same.
The y1 and y2 are the same, yes. The x1 and x2 are not.
Yeah.
So let's start to fill in, instead of up, down, left, and right, let's start filling in y1s, x1s, y2s, and x2s. Okay.
Well, I'm just saying technically you wouldn't have to do y1 and y2 since in this they're the same. Like, couldn't you just put like y, because you said we're going to do a systems equation.
Could you, yeah, I guess technically you could use the same. Let me try it the way I've done it before and then think about that after so I don't end up
Okay.
painting myself into a corner I don't know how to get out of. But yeah, technically they are the same. So what's the forces pulling up here?
Y1.
Y1. Anything else?
Y2.
Y2. So they're both working, and they're working together. So how do you think you would represent Y1 and Y2 working together?
2Y.
Well, using the notation we have up
Y1
here.
plus Y2.
Yeah, Y1 plus Y2. Okay, maybe you could make it 2Y. I just have to think about it. I mean, it should work, but. All right, so we got the two forces pulling up, and that's equal to the force down. What's the force down in this problem?
1,200 pounds.
Yep. Okay, what's the force pulling to the left? X1. And what's the force pulling to the right?
X2.
X2. Okay, so here's our two equations. This was kind of the initial draft. Now we've kind of refined it a little bit to start looking more like sides in a triangle. Now what we have to do is somehow get these angles involved. Okay. We got to use the 30 and the 45. So let's start with y1. What trig function, actually even before we do that, what's this angle down here?
30.
Yeah, we have two parallel lines, we have a transversal, so the alternate interior angles are the same. And this angle is also 45. Okay, so now, using this 30 on the inside, what trig function could we use to write a formula for y1, and it needs to use t1? Yep.
Sine of 30
So-
equals
Let's write this off to the side. Sine of 30 equals,
y1 over t1.
yep, y1 over t1. Now I want something I can substitute in for y1.
1200 minus y2.
Well, based on that formula.
Probably we'll just switch it up.
Yep,
Would it be T1 times sine 30 degrees?
yep. We're going to do 4 of these, and they're all going to look something like that. So y1 is t1 sine 30. Let's do y2. Kind of following the same pattern. Anyone think they can see what y2 is? Yep,
T2 sine 45.
T2
sine.
45.
Yeah. Runs as f off cosine cosine. No, that's for either Joe's.
How about x1?
T1 cosine. Or yeah, T1 cosine of 30.
T1 cosine 30. Yep. Anytime you want to calculate a horizontal, it's always a cosine. Anytime you want a vertical, it's always the hypotenuse times the sine. Okay, and what about x2?
T2 cosine 45.
It's going to be T2 cosine 45. Yep. Okay, so that was the trig part. Okay, so this problem really has three parts to it. It has kind of the physics part. We have to think about up equaling down and left equaling right. Then we've got the trig part, where we're figuring out all the sines and cosines. Now the algebra part is to substitute that in and solve it. So we've got y1 is, just look them all up, t1 sine 30 plus y2 is t2 sine 45 equals 1200. Okay, that's your first equation. Second equation, t1 cosine 30 equals t2 cosine 45. That's the system of equations we have to solve. Two equations, two variables. The easiest method would probably be substitution. Which equation is it easier to get a t1 or a t2 by itself? We'll call this equation 1 or equation 2.
T1 and T2 on equation 2 are like already by themselves.
Well, I need like this by itself. I need t1 equals, so I can like plug it into the top. Or t2 equals, yeah? Yeah, equation 2, you can do one thing. Which one do you want to get by itself? T1 or T2?
T1.
T1. Okay, so based on that, what would T1 equal?
Whole term on the right divided by cosine 30.
So T2 cosine 45 divided by cosine 30.
I thought you had to do the inverse cosine to do that.
No, we're not solving for an argument. We're rearranging because we don't have any variables in the argument. At some point, we need to change these to decimals now. Okay, we gotta start getting some decimals, and we'll round them. Okay. Now, I've got a formula for T1. What am I gonna do with that formula?
Plug it into the top equation.
For which variable?
T1.
Yeah, I'm gonna take this. We're gonna fill it in right there, and we're gonna solve for T2. And once we get T2, then we're like 95% done. Then we just plug it back in and get T1. All right, so T1 is T2 cosine 45 divided by cosine 30. So I got that part filled in. Fill in sine 30. Plus T2 sine 45 equals 1200. Okay, we can type that all into a calculator and see what we get. So cosine 45 divided by cosine 30 times sine 30. So it's 0.408. Okay, 0.408 T2. Okay, sine of 45. What's the sine of 45 to 3 decimal places?
2 pi, right? 3 pi, sorry.
Like when sometimes we see the number 0.866 a lot, that comes up with 30s and 60s.
0.701 or something.
707.
707.
Yeah. So that's 0.707 T2 equals 1200. Okay. What can I do now?
Combine like terms.
So combine your T2s, 0.408 plus 0.707. That is 1.1, we'll say 1.115. T2, 1200. And my last step to find out the tension in cable 2.
Divide by 1.115.
Yep. So I need 1200 divided by 1.115. Okay, so the tension in cable 2 is 1076.23.
Do we have a unit?
My physics is a little rusty, so I'm not sure what the unit would be like for force. Usually you use newtons, but this is pounds. Pounds
Forge.
weight. I'm not sure the unit, so we'll just go with the
Yeah, you
number.
have to change the 1,200 pounds to like
Newtons or something. Yeah, we're not gonna do that. So that's T2. So how do we get the tension in cable 1?
We just plug that into the second equation that we originally had.
I would even plug it into the one that we rearranged rather than the original because it's already got T1 by itself. So multiply by cosine 45 and divide by cosine 30. So multiply by cosine 45. What did I say? Divide by
Cosine 30.
cosine 30?
Yep.
So the tension in cable 1 is 878.74. What was it? 878.74. Yes, if this was a real like physics problem and you were doing it, yeah, you need to be a little more careful with your units. I'm more concerned about the number than I am the unit. Okay, and that's pretty much how you solve one of those every time. It never changes. After a while, you can kind of just jump, I think, right to this step because you already know up equals down and left equals right. As long as you understand how to do these quickly in your head, that's the only trig in the whole problem. Then it's just algebra. But that's how you do it. Okay, so that's the application that we're going to look at for vectors, the velocity vector and the force problem. Yeah.
Explain how you got T1.
T1, I just filled in T2 into that formula right there. And then I just divided by cosine 30 and multiplied by cosine 45. Okay, let me just double check. If I get that over to right, I'm really going to so that's the homework for tonight.
What do you mean by 57?
So 24 to 47 odds, and then 55, 57, and 66.